Welcome to this explainer, where we're going to unpack the invisible laws of physics that literally govern our everyday lives. I mean, have you ever wondered why opening a heavy door is a total breeze if you push near the handle, but almost impossible if you shove it right near the hinge? Or why you feel completely thrown outwards on a spinning merry-go-round? Well, today we're demystifying those everyday forces. Let's get right into it. Here's our roadmap for today. We'll start with the turning effect of force, move on to couples, and then hit the principle of moments. After that, we're finding the center of gravity, looking at the circular motion shift, and finally wrapping up with the centrifugal force illusion. All right, section 1, the turning effect of force. So, this fundamental principle actually solves that exact door problem I just mentioned, why they're so incredibly stubborn when you push near the hinge. In physics, the moment of a force, which you probably know as torque, is simply the product of the magnitude of the force and the perpendicular distance from the axis of rotation. But what does that mean in plain terms? Well, it's not just about how hard you push. It's absolutely crucial where you push. A greater distance means you need way less force to get the exact same turn. It's like a mechanical cheat code. Just notice the difference here. If you push a stationary ball right through its center, it just rolls straight forward, right? That's linear motion. But when a body is pivoted at a central point, applying force tangentially to the rim creates rotational motion. The pivot basically traps it from moving forward, so it transforms all that push into a spin. Okay, moving right along to section 2, couples, which is all about two forces combined. You know, what's really interesting here is that a single force actually isn't enough to perform a ton of common tasks. Seriously, try turning a water tap or twisting a key in a lock using just one finger pushing in a straight line. You literally can't do it. You actually need a pair of equal and opposite parallel forces working together. In physics, we call this dynamic duo a couple. The next time you're out and about, think about how often you intuitively apply these couples to create rotation. I mean, whether you're driving a car and pulling down with one hand while pushing up with the other, or riding a bike and pushing opposite pedals, these couples are absolutely everywhere in our daily routines. We use them constantly without even thinking about it. Up next is section 3, the principle of moments. So the crucial takeaway here is the comparison between static equilibrium, where things are perfectly, completely still, like a book just resting peacefully on a table, and dynamic equilibrium. Now, dynamic equilibrium is super fascinating. The object is actually moving, but the forces perfectly balance out to maintain a constant speed. Think of a raindrop falling at a steady terminal velocity, or an airplane just cruising along at a constant altitude. Same physics, completely different vibes. Imagine you're at a playground, trying to balance on a seesaw with someone who's heavier than you. You instinctively know they need to sit closer to the pivot, right? Well, the math proves exactly why. Equilibrium is only reached when the clockwise and anti-clockwise moments equal each other exactly. It's this perfect mathematical harmony of weights multiplied by their distances from the center. Which brings us seamlessly to section 4, finding the center of gravity. Now, for regular, uniform objects, finding that balance point, the spot where the entire weight of a body is considered to act, is pretty straightforward. As you can see, for symmetrical shapes, the center of gravity comfortably corresponds with the object's geometric center. So a rod balances right at its midpoint, and a disc balances right in its exact middle. Nice and easy. But what if the shape is completely irregular, like, say, a jagged, random piece of cardboard? You can't exactly just eyeball where the center is. We have to rely on a physical test to find exactly where all those forces balance out. And this brilliantly simple plumb line experiment breaks the whole solution down into 4 easy steps. By freely suspending the object from a few different edge points and drawing a line down a weighted string each time, you're basically letting gravity do the math for you. It magically reveals the balance point exactly where those drawn lines intersect. Pretty cool, right? All right. Shifting gears entirely, here is section 5, the circular motion shift. Okay, watch out, because here is a bit of a physics trap. Even if a particle is traveling around a circular track at a perfectly constant speed, its continuous change in direction means its velocity is technically accelerating. Yeah, you heard that right, because velocity includes both speed and direction. Any change in direction is an acceleration. It's kind of wild to wrap your head around, but it is absolutely crucial for what we're looking at next. And that takes us to our final and definitely most mind-bending part of the explainer, section 6, the centrifugal force illusion. To really understand the illusion, we first have to define the reality. Centripetal force is the very real, measurable, inward force that is required to keep an object moving in a circle. It's constantly pulling it towards the center. Think of the physical tension on a swinging string tied to a rock, or even gravity holding the moon in orbit. It's the tether holding the whole system together. Now, it's super easy to observe this inward tethering tension when you're safely on the ground just watching something else spin. But imagine you are the one standing right in the middle of a spinning merry-go-round, watching a ball tied to the center. What do you actually experience? Comparing these two perspectives reveals a fascinating disconnect. The observer standing safely on the ground, they see the true inward centripetal force provided by the string. But the observer rotating on the ride, they see the ball as completely stationary relative to them. So to explain why the string is tight without the ball moving any closer, their brain invents a completely fictitious outward centrifugal force just to balance the equation. And this perfectly explains why that intense outward push you feel, the one pinning you to the wall of an amusement park ride, is purely an illusion of physics. It's entirely created by your own rotating point of view. In reality, your body just wants to travel in a straight line, and the ride is continuously pulling you inward. So, to wrap up this explainer, I want to leave you with a bit of a provocative thought. If centrifugal force isn't actually real and is simply a byproduct of your perspective, how much of what you physically feel every single day is just an illusion of your frame of reference? Keep that in the back of your mind as you step back out into the moving world today.